All right, ladies and gentlemen, welcome back to another video with Mr. Kenton with AP Chemistry, and we're going to be finishing up the second half of topic 5.3, which looked at changes in concentration with respect to time, and we're going to be looking at it from a perspective of half-life and how we can use half-life to help us determine reaction order. Right now, again, we're going to start with the definition, and then we're going to work our way through the equations and the expressions we can use to help us determine the half-life. So let's dive right in. So first thing we need to recognize is that the half-life, now you've probably heard of this before, probably when you're thinking about like radioactive decay, when you think about isotopes and things like that. And it's very similar here. It's the time it takes for the concentration of a reactant to drop to half its original value, right? So time interval elapses, and then we get to half of the reactant concentration. Another time interval elapses, and you see how much time did it take for it to reduce by half, right? And so understanding half-life, we can actually look at it from a perspective of what happens with zeroth, first, and second order processes. They're going to follow a very specific pattern here on this idea of half-life. Now, when we talk about first order processes, right, half-life T1 half is going to be the time taken for A naught to reach half the value of A naught, right? And so for a first order process, we see that T1 half equals the negative ln of 1 half divided by K, where K is the rate constant. Now, this is on your reference sheet, and the reference sheet even is so kind enough, they go ahead and tell you, all right, ln of 1 half has a value of, negative ln of 1 half has a value of 0.693. So that's provided to you on the reference sheet. And just as a reference, things like radioactive decay are first order processes as well. Okay, so just kind of keep that in the back of your mind. I know that we did an example in class where we looked at that, but just remember that. So this is the half-life equation that you're provided. However, there are two other half-life expressions that can be used for second and zeroth order processes. And so for second order, that equation is T1 half equals 1 over the rate constant times the initial concentration. And then for zeroth order, it's half-life equals the initial concentration divided by 2 times the rate constant. Now, please keep in mind that for second and zero order processes, that is going to be concentration dependent, right? Whereas for first order processes, the concentration isn't going to play a factor in that particular part, okay? So we've got these expressions that we can use to help us generate half-life information for a reaction. We can use this information to figure out rate constants or things like that. We can also use graphical data to help us identify whether or not something's first, second, or third order based on these expressions that we've been given here, right? If we look at graphs, we should be able to make a conclusion about what type of process we're dealing with. Okay, and again, that's what we're going to be able to do is not only do you want to be able to use those equations, but we also want to be able to take a look at graphs and be able to identify what's going on here. Okay, and so on the slide that comes after this, there's going to be a graph, and it's going to show us these general trends that we would anticipate to see for all zeroth, first, and second order half-life processes. So if you've been given half-life data and it's a zeroth order reaction, which is going to show up on the next slide in blue, what you're going to see is there's going to be a decrease in the half-life. So the time it takes for the half-life to change, like that time period, is going to get smaller, right? For first order processes, what we're going to see is that for a first order process, it's going to show a constant half-life. So it's going to occur at a very consistent time interval, right? Let's say something has a half-life of 50 seconds. So for a first order process, it's going to be 50 seconds reduced by half. Another 50 seconds go by, another half is reduced. 50 seconds go by, another half, right? And then for our second order processes, what we're going to see is that there's going to be an increase in the half-life. So it's going to start off, it might be relatively fast. Maybe it starts off at 50 seconds. But as time goes on, let's say that 75 seconds elapse, and then the concentration is reduced by half. So now we've seen an increase. And then you allow more time to go by, and it takes longer for it to decrease by half. And then we see that 150 seconds have gone by. And so that's the type of thing that we would anticipate seeing for something that's second order. We should see that the half-life is going to get longer for a second order process. And the next slide is going to have a graph on it that we're going to be able to take a look at that's hopefully going to be able to drive that point home for us. All right. Now, here is that graph that I was referring to, right? And so on our graph, it's going to be important to recognize that we have several pieces of information. So we've got a blue curve, we've got a red curve, or a blue line, a red curve, and a yellow curve, right? They're telling us what order they are respectively, but I want us to try to put together kind of the information that we were talking about. Now, for all of these processes, notice that the concentration versus time, the initial condition is at 5. And so if we wanted to undergo a half-life, we would need to look at the data point at 2.50. Now, looking at the graph, the time or the concentration intervals are 0.125. So we've got 2, that's 2.125, 2.25, and so it would be at the fourth one, so 1, 2, 3, 4. We should be roughly right here at 2.50, right? Half of that's going to be at 1.25, so that's going to be here. It's going to be at this second line, and then at half of that, 1.25, would be 0.625, which would be at the fifth line in this next one, so it would be 1, 2, 3, 4, 5. So it would be at 0.625 here, right? So that's at this spot, and this spot respectively, right? And so what I'm going to try to do, ladies and gentlemen, is show you the half-life data and look at the timestamps to show this particular point that, yes, we've got those trends that we were looking at on the previous slide. So if we follow this for the blue line, right, if we follow, and I apologize if my hand isn't steady, right? If we track it to there and we go down to our time interval, right, we can see that the first half-life occurs at 10,000 seconds, right? If we come over here, we follow our line, it hits there. It's looking like that it hits somewhere down here. Now again, I apologize for my lines, but bear with me. And then for our last data point, it's going to hit right around here. And so comes down there. And so what we start to see, ladies and gentlemen, is we can see that for this zeroth order process, we're seeing that the half-life is getting shorter. It went from 10,000 seconds to about a little over 5,000 seconds. And then it was like 1 to like 2,800 seconds, right? So like we're seeing that shift in the half-life that we would anticipate being able to see. All right, well, what's going on with our first order processes? All right, so same line. Obviously, it's going to get kind of messy here. So just kind of bear with me. So that's actually, instead of making it messy, let's just erase the ink. Right, we can erase our blue line. Actually, I'm going to keep it. Right, so we can go at this same spot, say, okay, it hits right here. And so then we can come down and say, all right, there's our first half-life. Right, now at 1.25, we do the same thing. Follow our line. Bam, we found our next half-life right here. Comes down. And then our third half-life is going to hit right here. Right? And so what we start to see here is it's a pretty consistent step. Obviously, I don't know the specific numbers, but let's say that's 2,800, that's 5,600, and then that would be, oh, if I'm doing my math right, 7,400, something like that. And so, or yeah, something like that. So what's that? 6,000, 7,000, 8,000, sorry, 8,400 or something like that. Right? So we're seeing a pretty consistent time interval of where that's taking place. Right? So that's showing that trend that we anticipate for something first order to have a consistent or a constant half-life. Right? That's not concentration dependent. All right. And then our last one here, right? If we're following along with our yellow curve, our first half-life happens right here, right? Our second half-life is going to occur right here. And then our third half-life is going to be right there. So we can already see that our first time interval was about 900 seconds, but then it was 1,000, 2,000, like 2,400 seconds. And then it went from 2,400 seconds, we got 3,000, 4,000, 5,000, we're right at like 5,600. So we're seeing that that half-life is increasing. So that's just a way that we can look at that and say, okay, the terms that the information we were just given, that matches up with what we just communicated. Hopefully that makes sense, and if you need to watch this again or pause at any point, feel free to do so. All right, so let's take a look at a couple of examples, right? And I know that we worked these out yesterday in class, but it's always good to do example problems and just to kind of refresh our minds with what we're going to do, right? So the first question, it says a first order reaction has 1/16 of the original amount left over after 500 seconds. What is the half-life of the reactant in this reaction? All right, so they simply want to know, the question is, what is T1 half? Right? Now, they haven't really given us any rate data or anything like that, but they have already told us two big pieces of information. They told us that we had 1/16 of the original, and the total time that elapsed, so T total, was 500 seconds. Right? And so what I would do to try to figure out the half-life, I know the total time. I just need to figure out how many half-lives have occurred during that time period if there's 1/16 left. So T1 half would be equal to my T total over number of half-lives, right, that took place. So T total was 500 seconds. And then the number of half-lives, we can see, since it's 1/16, that means that 4 half-lives took place. So that means that this process has a half-life of 125 seconds. Okay. So again, they ask us for half-life. They tell us we have 1/16 of the original amount. They told us the total time that elapsed. So we just take the total time, divide that by the number of half-lives that occurred, and that'll give us our half-life for that first one. All right, the second one, however, is not so kind to us. It's a little bit trickier, right? They tell us that we have 93.75% of a radioactive isotope of technetium-99, technetium-99, it remains after 24 hours. And they want to know, what is the half-life of technetium-99? Okay, and so like when I look at this, I have several key pieces of information. I know that I have an AT value, right? That's going to be my 93.75%. Let's just assume that it's grams. So we got 93.75 grams. I've also got initial conditions, because we're assuming A naught would be that we started with 100 grams. And what we have is a T value that's 24 hours, right? And so they want to know, what is the value for T1 half? Now, at first glance, you might be looking at that and you might think, Mr. Kent, I've got all the information I need. I just need to know what order is this so that I can figure this out, because I don't know K, so I can't just simply plug in the half-life equation. I also don't know what order it is. Now, if you remember what I said earlier in the video, if we have something that's a radioactive isotope, that means that it's going to be first order, right? So if you have radioactive decay or anything like that, it's going to be a first order process. So if that's the case, then in order to figure out T1/2, the first thing I'm going to have to do is figure out K. And to do that, I can use my integrated rate law for first order processes. So I'm going to need to use the ln of AT equals negative KT plus ln of A naught, right? And so from there, I should be able to figure out K. So if I plug in my numbers, what I'm going to have set up is I'm going to have ln of 93.75 equals negative K times my time, which is 24 hours, plus the natural log of 100. So the ln of 93.75, that's going to give us, I'm just going to do this for simplicity's sake, that's going to give us 4.54 equals negative 24K plus ln of 100 is going to be 4.61. So if I wanted to get K, because I want to make sure that I don't miss anything, I'm going to erase all the information that we know now, right? And because I want to show all the steps here. Right, we're going to end up with 4.54 minus our answer. So we end up that negative 24K equals negative 0.0645. We're going to divide both sides by negative 24. And so then K is going to be equal to 2.69 times 10 to the negative third. And because it's first order, this is going to be hours inverse, right? Because that has to be the units for our rate constant. All right. So now that we've identified K, we can then go through and we can say, all right, I can now figure out my half-life. I can figure out my half-life by using the first order half-life equation that's provided to us on our reference sheet. So we're going to use that information that we just found. We're going to say, all right, I know that T1/2 equals 0.693 over K. So then we got 0.693 over 2.69 times 10 to the negative third hours inverse, right? And so we got 0.693 divided by that. And we're going to end up with that we're going to get a half-life that's approximately 258 hours for technetium. All right. Hopefully that was insightful. Hopefully that makes sense. All right, and then like I mentioned yesterday, this was kind of like a little cheat sheet that you can use at the end. And really, I think the most important thing for you guys to focus in on would be everything below the differential rate law. So you can see if something's zeroth order, this is what you would expect to see on a concentration versus time graph. If it's first order, this is what you're going to see on a concentration versus time graph. If it's second order, this is what you're going to see on a concentration versus time graph, right? And notice the biggest difference between this one and this one. You've got a steeper exponential here, and it's getting closer to that 0 value. You've got your integrated rate laws that have been provided to you. You've got your plots that show when you get a straight line and with respect to what units. So this one, it's concentration versus time. This is our natural log of concentration versus time. And here's our 1 over concentration. You've got your negative slopes for the first two, positive slope for the second. You see how changing the rate or changing the concentration impacts the rate. You got your half-life equations, and then you've got your units for your rate constant, right? And so that, ladies and gentlemen, covers everything in topic 5.3. I hope this video was insightful, and I look forward to seeing you guys again soon. Take care.